Number 7 asks you to find the limit of this fraction as x approaches infinity. So if you just plug in, you can first check. You'll get pi squared minus pi squared plus 0 over negative 0, which pretty obviously equals 0 over 0, which is undefined. So the problem is asking you to use the L'Hopital rule, which is something you just need to know off the top of your head. So if you don't remember, the rule basically says you need to take the derivative of both the numerator and the denominator unrelated to each other. And then once you solve that, re-plug in your initial limit, and then that will give you, that's the answer to the problem. So if you do this real quick, you're going to get 0 minus pi plus cosine of x over negative cosine of x. And then if you re-plug in, you'll get negative pi minus 1 over 1. And that's going to be your answer. Simple as that. Problem 8 is asking us to find the area under a curve again. But if you notice, this is a quarter of a circle, and we also are given the radius versus an x or y coordinate. So this differential that we've been using, dA equals dx dy, is probably not the best choice. We'll have to use the differential for a polar system, which is dA equals r times dr d theta. We'll have to now find our limits, which are really simple. For the r coordinate, it's going to be 0 all the way to r, which they give us. And then for theta, we're only going from 0 to pi over 2. And then we're just going to solve this differential. Solve this integral, excuse me. And then you'll find the area equals pi r squared over 4. And this makes sense because if you think about what the area of a circle is, it's pi r squared. You only have 1/4 of your circle, therefore you have pi r squared over 4. Problem 9 is another integral we need to solve, but this one's unique because of this point of intersection will flip which equation we're using as our top limit. So we'll have to do 2 separate integrals for this problem. We'll have to find 2 sets of limitations. So for x, the first will be from 0 to this point of where x equals x squared, which is going to be 0 to 1, just like before. We've done a problem similar to this. And the second set of limitations for the x variable is going to be from 1 to this dotted line of x equals 2. For y, for the first set, the bottom of our limits will be x squared to x, and then the inverse will be true for the second half. It will be going from x to x squared. When you're setting up your integral, it's very important that you use the correct limitations. So for this first integral, which is going to be this shaded region right here, I'm highlighting, your x will go from 0 to 1, and your y will go from x squared to x. And the second integral, which is the second shaded region right here, it's highlighted in green, is going to go from, for the x variable, 1 to 2, and from the y variable, you're going from x to x squared. Now we're going to take a moment and solve this integral. All right, once you solve that integral, you'll find that you get an area of a equals 1. Problem 10, we're finding volume under a curve rotated around the x-axis again. So as you can see with my hand-drawn graph down here, I've switched our coordinate systems from Cartesian back to cylindrical, and x has become z, y has become rho, and we've added theta as our rotational coordinate, which means we're also going to use the differential dv equals rho, d rho, d theta, dz again. We have to find our limits, which for our rho axis is going to be 0 to root 7, which is our boundary equation of this curve. Our z coordinate is going to be 0 to 4, which was a given to us. And then again, we're going all the way around, so theta is simply going to be 0 to 2 pi. And we're going to have to set up our triple integral again. 2 pi, 4, and root z are top limits. And 0, 0, and 0. And we're going to take a moment and solve this integral. As you can see, the answer is v equals 8 pi. I think starting from this differential is the simple solution to these kinds of problems, but there is a second method called the disk method, which you've probably learned about already. All this method is essentially, instead of starting with each variable and integrating from there, you're assuming that this is a volume made of infinite disks, infinitely thin disks, and then you're integrating the area of each of those disks over the length of your function, and you're finding the same volume answer. What we need to know is this is the formula you're going to start with for a disk method problem. Pi over the integral, pi times the integral of your function trying to resolve squared, and then your variable is the variable that's dependent on that function. So for this problem, you would just have v equals pi. You're resolving from 0 to 4 is your x, and then our function that we're resolving is root x squared dx. And if you solve this integral, you'll find that you have a really simple solution of pi times 1 over 2 x squared from 4 to 0, and you get 1 pi over 2 times 16, which gives us the same answer of 8 pi. And you might think that this integral is really simple, and it is. That's why the disk method exists. I personally prefer to just start from the differential. And if you get a situation where the formula you get is strange, or it's a very strange shape or strange way to rotate, I personally think it's easier just to start from dv equals rho, d theta, dz, and build my whole equation. If you have a really simple problem like this, it's probably easier just to start with your disk method equation, plug in, and do a really simple single integral to get your answer.